Hey audience! Last time we talked about a way to use tokens to do addition in a way that felt a bit easier than the way that we normally add. The problem was that when we wanted to do multiplication, we had to do a lot of conversions from decimal numbers to these sort of binary piles, and that took a while. As we were trying it out, we decided that it would be better if we could start by converting the numbers that we wanted to multiply into these piles first, and then do the multiplication itself using these tokens, instead of just using the tokens to add. So let's do the same multiplication from the previous video and start by converting the numbers into tokens. So how can we multiply these as they are now? Maybe we can do something similar to what the Promptuary does. So let's lay these out in this sort of rotated L shape, the same way that the digits will be laid out when using the Promptuary. The Promptuary lines up the digits against a grid, and each grid cell has the product of the digit in the column and the digit in its row. So we can draw out a grid to put our partial products into. And while we're at it, let's move these tokens from the top to the bottom, just to make it easier to work with. They're still in the same columns, so it should work out just fine. So now how do we get the partial products? Well, we could make more strips and more cover sheets like we did before. The paper strips encoded a multiplication table with their digit multiplied by any other digit, and the cover sheets exposed the one entry that we cared about. So let's start by looking at the binary multiplication table, which looks like this. We can see that we never have any carry digits, which means that we don't need to split each entry into a separate carry and units part. The 0 paper strip would just be completely blank, since 0 multiplied by anything is 0. And the 0 cover sheet would just cover everything up for the same reason. The paper strip for 1 would have an entry for multiplying by 0 and multiplying by 1, but since the 0 cover sheet just covers everything up, we can leave off the multiply by 0 entry from the 1 strip. Then the cover sheet for 1 just shows that one entry on the strip that's underneath it. So the 0 strip is blank, the 1 strip is just all 1s, the 0 cover sheet is blank with no holes, and the 1 cover sheet just shows the one and only entry on each of the strips underneath it, so it might as well just not even be there. So by now we've noticed that we're just wasting our time with the paper strips and cover sheets for this binary Promptuary. We can just skip straight to placing tokens down by putting tokens wherever a row with a token and a column with a token intersect. 0 times anything is 0, so every row with a 0 must be empty, and every column with a 0 must be empty. And the largest value you could possibly get from multiplying two binary digits is 1. There are never any carry digits, so 1 token goes wherever the row and the column are both 1s. We can label each of these grid cells with their values now in order to get to adding our partial products. If we multiply the number that each row represents by the number that each column represents, we can find out what value a token in that cell represents. This is the same as the Promptuary. We have, for instance, a tens row and a hundreds column, and at their intersection we have thousands, which is 10 times 100. We can see that the diagonals all have the same values. This is why we were adding along the diagonals earlier. In the Promptuary, every digit within a diagonal had the same order of magnitude, or power of 10. And here, every token within a diagonal has the same order of magnitude, or power of 2. So just like last time when we had piles of tokens in bins to represent a number, now we have piles of tokens in cells to represent our answer. And if we set aside the tokens for the original numbers that we multiplied, all the numbers on the board taken together represent a single number, which is our product. We could just add the token values like this to reconstruct our answer, but we can do even better. Since any cell along the same diagonal has the same value, we can freely slide any token along its diagonal without changing the result. So for instance, the number represented by these tokens is the same number that's represented by these tokens. But when one token runs into another and we have two tokens on the same cell, we find ourselves in the same situation that we had earlier with our addition. We can abbreviate this pair of tokens into a single token in the next diagonal, and it still represents the same number. So let's just let all of our tokens slide down these diagonals, and we'll abbreviate whenever they touch each other. Then at the end, we'll have a nice single row of tokens and fewer tokens to add up to recover our answer. And that leaves us with significantly less conversion than we had last time, which is the goal. And if we wanted to take this result and multiply it by another number or add another number to it, we can just leave it in this tokenized form to save even more time. So now we've condensed the entire process down into a set of rules, a set of moves that you can make in this game. You line up your numbers and place tokens at the intersections. Tokens slide diagonally as much as they want. Two tokens that meet can be abbreviated into one on the next diagonal, either to the left or upwards. One token can be extended into two tokens on the previous diagonal, either to the right or downwards. And as long as you follow these rules, the number represented by the tokens on the board is always the same. It's invariant. And these rules let us manipulate and play with a number in ways that we couldn't with the Promptuary. We can start with tokens at intersections and collapse them into a single row, or we could move tokens from a single row into a pattern of intersections to do division or even square roots, but maybe that's for another video. So I've been talking about these numbers as being binary because it's convenient sometimes, but I also mentioned in the last video that I think it can be useful to not think of these as binary numbers. And the big reason for that is that binary is, well, a number system. And the point I really want to make here is that we're not working with numbers anymore. Now we just have tokens and movement rules, which are easier for us to work with than numbers. And the arithmetic is encoded in these rules. The rules are the arithmetic. Abbreviation is carrying. Extending is borrowing. Putting tokens at intersections is multiplication. We do have to convert our inputs from numbers and then convert our outputs back into numbers, but in the meantime, numbers could not be farther from our minds, even though arithmetic is happening the entire time we're moving these tokens around. And that's what kind of fascinates me about the location arithmetic even more than Napier's bones or Promptuary. You do end up with a bit more work to do in the end with all these conversions, but the process itself has really completed the task of offloading computation from our brains and into the physical world. And that's fundamentally what computing devices are. Rules acting on things that just happen to give you the same result that you would have gotten if you'd been working with numbers. You have mechanical forces acting on gears and levers, gravity acting on dominoes or marbles, electric fields and heat acting on electrons, or a set of board game rules that a person plays out on tokens. And then one more thing. Take a look at this schematic for a high-speed digital multiplier. It should look pretty familiar. One input comes in rows and the other input comes in on columns. These AND gates output ones whenever both the row and the column inputs are ones. So that handles the intersecting rows and columns rule. And then these adders here do the rest. If only one input to the adder is activated, which is like having one token in the cell, then the signal passes straight down to the next row, which is just like sliding a token down a diagonal. If two or more inputs to an adder get activated, the signal gets passed out the carry output to the next column over, which is like abbreviating. So this high-speed multiplier circuit is doing the same thing as this multiplication method from the early 1600s. I think that's pretty neat. I didn't really know where this series was going when I started it, and I still don't really know, but I think there's some insights to be found in knowing how different mechanical computation devices work. So I think I'll dive into those some more. Maybe I'll talk more first about how Napier's devices could be used for division and square roots. Who knows? We'll find out together in the next video. I'll see you then.